And share. Oh, that's what I forgot to do. Oh, got another person here. Xavier, that's great. All right, so I want to present my screen. Share.
We can see it. I can see it.
Yay! Thanks.
Yeah.
It's awesome. Okay, good. Applications of the cross product. So I think this is pretty straightforward. I think you'll find it pretty straightforward. So we're learning to apply the cross product to find the area of parallelograms and triangles. That's pretty easy. And apply it to find the, apply scalar projection, together with the cross product to find the volume of a parallelepiped, which is cool. All right, so our first application is the area of parallelograms and triangles. So yesterday when we learned about the cross product, we learned that the definition of the magnitude of the cross product of two vectors arranged tail to tail is the area of the parallelogram it forms, which is pretty handy when you're trying to find the area of a parallelogram. So if we want the area of this parallelogram here, we just need the magnitude of the cross product of two of the vectors we can form that are tail to tail. So I might choose those two because they're tail to tail. And notice again, these are vertices here. So they're not vectors. They're just points in 3 space. And we want to make vectors out of them, point-to-point vectors. So the way I've chosen is I've chosen vectors SP and SR. You could have chosen like PQ and PS. Doesn't matter which two you choose, you would get the same area. The way I've decided to do it, my area is going to be the magnitude of vector SP crossed with vector SR. So that's what I would write down, the magnitude of vector SP crossed with SR. But now I need what is vector SP. So vector SP is going to be P minus S. That's how you get a vector from 2 points. So 3 subtract -2 is 5. -1 subtract 6 is -7. 1 subtract 2 is -1. And I'm crossing that with vector SR, which would be R minus S. So 0 subtract -2 is 2. 3 subtract 6 is -3. And 0 subtract 2 is -2. So I'm finding the magnitude of the cross product of those two vectors, which is going to be the magnitude of the vector. So I'm going to do my little 5, -7, -1. Repeat the 5, 2, -3, -2. Repeat the 2. Start 1 in, downward minus upward. Move to the right. And then to the front. And this step here I'm doing now, you don't need to show, but I'm just going to show it. So 14 minus 3. Most people did awesome. A few signs, but nothing major. So really good job, guys. -2 minus -10. And then -15 minus -14. Okay, and then close your parentheses and then your magnitude bar. So then this next step you do need, so this is once you found the cross product you should get, it's the magnitude of the vector 11, 8, -1. And then the magnitude of that vector is the square root of 11 squared plus 8 squared plus 1 squared, or the square root of 186. Now, because it's an area, you want to say that it's not, you have to add units, okay? You can't just say it's root 186, because if you leave units off, it's assuming they're linear units, but these are square units because it's an area, so you have to add on square units. Or I've had people in the past write like units with a little power of 2 here as units squared. Either of those is fine. But just make sure if you're finding an area, you put either square units or units squared with your number. And you can find it as a decimal if you want to. Okay, so you could do it approximately if you want to as well. You don't have to. It's approximately 13.6 square units. If you do find it approximately, make sure you put your dot above the equals. So that's the idea for finding the area of a parallelogram. You just have to use the vertices to make two vectors that are tail to tail. Find their cross product, find the magnitude of the cross product, and then you have the area. Okay, so determining the area of a triangle with vertices. Anyone have any thoughts?
You could do it the same way as the parallelogram, but divide by 2.
Right, so if I just made a parallelogram out of this, then I could see like the area of the parallelogram would be the cross product of HG crossed with HI. But then if I just want the triangle, I would divide that by 2. So I'm going to write that formula out. So the area of the triangle is going to be the magnitude of vector HG crossed with vector HI divided by 2, because it's half a parallelogram with those same basis vectors. So that's what we're going to do. So we have to find vector HG. So H was 9, -1, -6. So its vertice. The vertice for G is 7, 2, -5. And the vertice for I is 7, 3, -3. So HG vector is G minus H, so 7 minus 9, -2. 2 minus -1 is 3. -5 minus -6 is +1. Crossed with HI, so 7 minus 9. 3 minus -1 is 4. And -3 minus -6 is 3. Over 2. I often forget about the over 2, so don't you forget about it. So then we're going to do our cross product. So I'm going to do that at the bottom here, where I have room. So -2, 3, 1. Repeat the -2. -2, 4, 3. Repeat the -2. Start here, downward minus upward. Okay, I'm going to try to do this all in one step, my cross product here. So I'm thinking to myself, 9 minus 4 is 5 would be the first component. -2 subtract -6. -2 subtract -6 is 4. -8 subtract -6 is -2. Over 2. Is that what you guys got for the cross product? 5, 4, -2?
Yep.
Yeah.
Yep. Awesome. Good. Okay, so then we're going to take the magnitude of the cross product, so the square root of 5 squared plus 4 squared plus 2 squared over 2. So the area is the square root of, what is that, 25 plus 20, so 45. Square root of 45 over 2, and then square units because it's area again. Or you're welcome to find it approximately if you want to as well. Okay, so I feel like that's finding the area of a parallelogram or a triangle is pretty straightforward, as long as you know how to do the formula and you know how to find point-to-point vectors from vertices. The next one turns out to be easy too, but it's cool how you get to it. So a parallelepiped is a box-like solid, which opposing faces are parallelograms. Okay, so you can see like it's a box-ish shape with parallelograms for its sides. Okay, this is a prism. And we know from grade 9 that the volume, sorry, I'm going to write area there. The volume of any prism can be found by taking the area of the base and multiplying by the height. So that's just a formula for the volume of any prism. If we know the area of its base, multiply by its height, then we'll have its volume. So I'm just going to change volume to V. Do you guys see this as the base? Like if I color in here, is this the base of my prism?
Sure, yeah.
Yeah, does that make sense? And it's a parallelogram, and I know that the area of that parallelogram would be the magnitude of B cross C. Does that make sense? So this is the area of the base. I'm going to show this correspondence here. Now the height is a different story because the height is not the magnitude of vector A. Do you guys agree with that? Because the height is going to be perpendicular to the base. So the height is going to be like this measurement here. If I go perpendicular to the base, it's going to be like this. Just can you just hold on a second? Oh, stopped. Okay. Okay, so this is the height here, where it makes a 90-degree with the base as well. Now, how do we get that height? It turns out to be really cool. So if I do vector B cross C, I'm going to get a vector that's perpendicular to both B and C. Okay, so a vector B cross C is going to be perpendicular to both B and C. So if B cross C is like flat, I'll do my little picture on here again. Try to make it look like this. So here's B. And here's C. So B cross C is going to be straight up, right? Straight up, perpendicular to both B and C, and longer than them, okay? Because it's going to be linearly as long as the area of the parallelogram would be. So that's what I'm going to draw on here. I know it's hard to draw in 3 space and 2 space, but this vector here is going to be vector B cross C. So that vector straight up and down, perpendicular to both B and C, is vector B cross C. Now, we're going to use projection here. So if I project vector A onto B cross C, which means that I want the shadow of vector A onto vector B cross C. So my light source is coming perpendicular to B cross C. So here comes my light source. My light source is coming from this way. So the shadow of A onto B cross C is going to be, so here's where A starts. So this is part of the shadow, part of the shadow. The shadow of the tip is going to be here. So this highlighted part here is going to be the magnitude of the projection of A, vector A onto vector B cross C. And it also turns out to be the height of the parallelepiped. So if I go over to the height of the parallelogram is going to be the magnitude of the projection of vector A onto vector B cross C. So we've got volume is the area of the base, which is the magnitude of vector B cross C, times the height, and the height is the projection of vector A onto vector B cross C. So this is height right here, from here to here. So this formula looks complicated so far, but it's going to turn out to be really nice because, and this is a time sign, not a cross, so I'm going to kind of make it into a star so we don't see it as a cross. The formula for the magnitude of a projection is the magnitude of A dotted with the little one, which is B cross C, over the magnitude of the little one. So can you see if we're multiplying by B cross C and dividing by B cross C, these magnitude of B cross C's divide out? So we're left with the fact that the volume of a parallelepiped is just the magnitude of A dotted with B cross C. Cool?
So I suppose if all your vectors are coplanar, you're not going to get a parallelepiped.
Awesome. Right, because then A dot B cross C would be 0 and you wouldn't have any volume, right? Because they're all in the same plane.
There you go. Cool.
Yeah. So that's, the formula looks pretty complicated, especially like in the first step and then the second step, but then it ends up being a pretty straightforward formula to use. So we're going to try it. So in question 1, find the volume of a parallelepiped with sides determined by those 3 vectors. So our volume could be the absolute value of U dot V cross W. You can do whatever you like here. You could do V dot U cross W. We're taking the absolute value of it, so you'd get the same thing. I had maybe 2 or 3 people forget that when you have dot and cross, it's an implied order of operations, so you always have to cross first, okay? So some people were having a hard time with that yesterday. So we're going to take vector U and dot it with whatever V cross W turns out to be. So on the side, I'm going to do V cross W here. So V is 0 or -2, repeat the 0. I'm going to start here. So V cross W is going to be -16. Subtract -4, which is -12. -4, subtract 0. 0, subtract 8. And now we want the absolute value of that. So dot product, remember, is multiply and add. And no parentheses anymore, it's a number. So 2 times -12 is -24. -6 times -4 is +24. 2 times -8 is -16. And then when we add these up, we get the absolute value of -16 And what is the magnitude of negative 16?
16.
Just
Yes.
16.
So some people were having trouble. They got to one of the questions, they got to the absolute value of -7 and they didn't know what to do. So what that actually means is what's the distance from 0 to -16? It's 16, okay? 16 units. And in this case, they're cubic units because it's a volume. So the volume of a parallelepiped with those 3 basis vectors is 16 cubic units. All right, so a parallelepiped could be defined by the 4 points in space. They're being nice and giving you one is 0, 0, 0. So here's my vertex A, 0, 0, 0. Oops, I should put it like it's above it. So I'm going to try to make, here's my point A. I'll try to make it look like this picture-ish. Okay, but I'm just going to draw the 3 basis vectors instead of the whole thing. So this could be my B vertice and my C vertice over here, say, and then my D vertice up here. And A is 0, 0, 0, which is easy. B is 0, 5, 3. C is 1, 3, 0. And D is -3, 0, 0. Anybody want to make these into vectors? So I'll make this vector AB, the vector AC, and the vector AD as my basis vectors for the parallelepiped. So the volume is going to be the magnitude of, and then you can do whatever order you want. I'm going to do vector AB dotted with vector AC crossed with vector AD. And then I have to figure out these point-to-point vectors. Luckily, A is 0, 0, 0, which makes them really easy to find out. So AB is B minus A. But since A is 0, 0, 0, AB is just going to be 0, 5, 3. AC is just going to be C minus A, or 1, 3, 0. Crossed with AD. So the volume is going to be magnitude of 0, 5, 3 dotted with the cross product of these, which I'm going to do down here. Start here. So downward minus upward. 0 minus 0 is 0. Downward minus upward, 0 minus 0 is 0. Downward minus upward, so 0 minus -9 is +9. So this dot product should be fairly easy. So 0 times 0 is 0, 5 times 0 is 0, 3 times 9 is 27. And the absolute value of 27 is 27 cubic units because it's a volume. Okay, so if you're given vertices instead of basis vectors, you just have to make the basis vectors.
I'm wondering, Ms. Northwood,
Yep.
could you find the area of a triangle-based prism using this?
Yep. Yes, that's in the homework.
Yeah?
Yes.
Because I feel like that would be useful.
Yes, because well, you're actually going to find the volume of a tetrahedron.
Yeah.
And that's a sixth the volume of the parallelepiped with the same basis vectors. And that's I give you that formula in the practice.
Cool.
Yeah, it is cool. And I've got a little diagram there that shows how it fits in. Okay, so our third application is to check and see if 4 points in space are coplanar, and John already talked about this. So if you find, so yesterday we learned how to find if 3 vectors were coplanar. So for instance, we always knew 2 vectors were coplanar. So we'll put A down here. So if we did A cross B and got vector A cross B, which is my yellow pen, and then I dotted A cross B with C and got 0, then I knew all 3 vectors were coplanar. So similarly with 4 points, to see if they're coplanar, I can make 3 vectors out of them, deciding on which one I want to go from. So I could say I want to connect all my vectors to, I want D to be the start of all 3 of my vectors, point D. And then I'll make point E over here, point F up here, and point G. And we're seeing whether or not all these 4 points are going to lie on the same plane or not. So I want to make vectors DE, DF, and DG. And so I'll find the cross product of vectors DE and DF. And if that cross product is perpendicular to DG, then all 4 points are coplanar. If not, then they're not. So first let's find vector DE. And we want to cross it with vector DF. So vector DE is going to be E minus D. 0, 2 minus 1 is 1, -2. Crossed with DF, which is -4, 0, -2. And then I'm going to cross down here. Start in here. So DE crossed with DF is going to give me -2 minus 0, +8 minus 0, 0 subtract -4, which is +4. And now we're going to see what DG dotted with DE cross DF is equal to. So DG is G minus D, so it's 2. 1 minus 1 is 0. 3 minus 2 is 1. Dotted with our cross product here, which we found to be -2, 8, 4. And we get -4 plus 0 plus 4, which does give us 0. So we can say since DG is perpendicular to DE cross DF, then the points D, E, F, and G all lie in the same plane, or are all coplanar, all lie in the same plane. So same test as yesterday, except we had to make the vectors. We were given points instead of vectors. We had to make the points into vectors.
Now, if we had more points that we wanted to prove were coplanar, would we just dot products more vectors with the cross product we made?
Exactly. So you could find, for instance, John, that would probably be a good question if they gave you 5 points, then maybe 4 points would be coplanar and one of them's not, but they are all not coplanar.
Mhm.
Because
Okay.
it's usually an all or nothing question. It says, are they all coplanar? But yeah, that's what you would do. Okay, I'm going to stop recording. Stay on for a second because I want to just talk a little bit about the next lesson that that's pre-recorded. Stop recording.